for being late. I messed up the time. I'm very sorry because I'm on the East Coast. So with that, let me talk about good data and bad data, the welfare effects of price discrimination. This is joint work with Nima and Ali, who are here and are going to take all the difficult questions. So let me just tell you where we come from. I mean, recently, there's a lot of emergence of firms collecting consumer data to offer group-specific prices. And this is not even something that is very new. We kind of even knew from before that, like, if you want to buy like a airline ticket, if you go at 6 a.m., it's cheaper than if you go at like 3 p.m., like on a Friday, because everybody's buying, okay? But this, with the emergence of this huge new big data technologies, this has come at the forefront of policy. For instance, this is a letter that follows the Senate hearing on May 2nd, 2024. It's written to Amazon. It says large tech platforms have access to personal data that can be exploited by corporations to set prices based on the time of the day, location, or even the electronic device used by the consumer. So that raises the question of what are the welfare consequences of this data collection and using by companies. So let me give you two extreme points of view that exist in economics about monopolist use of data. And that these are both very prominent, and they come, if you want, you can think about them as the folk wisdom in economics versus the theory. The folk wisdom argues for bad data, and it comes from Pigu's like seminal work in 1920. Basically, the idea is no way information to the monopolist is always bad, because the price discrimination that follows unquestionably hurts consumer surplus. On the other hand, we have the much more recent influential work of Stephen and his co-authors, Dirk and Ben, and I'm going to call it BBM going forward in 2015, and they argue that, okay, there is always an information that given to the monopolist, the price discrimination that follows improves consumer surplus compared to no information. So in a sense, they're arguing that, okay, data is not like always bad, okay? While Bigu was like, data is always bad for consumers. So how to reconcile these things? On the surface, they look like super like opposite each other. So let me start giving you some thought of like, okay, where did this like influential work of Pigu rely on? Let's take two demand curves. And basically what Pigu does in his seminal work is that argues that if there are two demand curves, giving price discrimination, which he models as giving full information, is always bad for consumers. How do we see that? At the bottom, there is the case where there is no segmentation, meaning if there is possibility that like the 50%, the demand curve is 2 minus P, 50% is 3 minus P. These are both demand curves as a function of price. Now, if we don't segment them, then the monopolist faces the bottom demand curve, okay? So it's basically the addition of the two demand curves, we face half and half. And then if we don't segment, then he's gonna choose the optimal price to be 1.25, and he pays 2.5, and he sells 2.5 units. Now, if he has full information of this is the first group of consumers and that is the second group of consumers, then he can price discriminate, and that's segmentation. So to consumers who have a lower demand curve, he sets a price 1 and he sells quantity 1. To consumers that have a higher demand curve, so he sets price 1.5 and sells quantity 1.5. And you can see we highlighted the consumer surplus in each of the curves, which is the area below the demand curves where consumers buy. And believe me, that the area below the demand curve, when there's no segmentation, is higher. In fact, another thing that you can observe in this figure for going forward is that the quantity sold in the two cases is the same, okay? The quantity sold in both cases anyways, 2.5. The difference is that when there is full segmentation, people who had a lower demand curve are charged less. People who had a higher demand curve are charged more. So that is all that this difference comes from. Now, what in light of that seminal result, what do we do? First, we strongly believe that sellers might have partial information, while, as I said, Piku's work relies on full information about customers. And that this view comes from this regulatory question of, well, that I showed you in the first slide. Should sellers be allowed to collect information when this information is partial? We don't know how much they get. We don't know what they can get from the sales of consumers and transactions. Second, it's extremely hard for the regulator to monitor and control the existing additional information of the monopolist. Okay, it's very hard to say this platform has this much data is relevant, this is what it's collecting. So it is an important first order question to think about. When does the answer to this question of whether data is good or bad does not depend on the existing additional information. And that is what's called information is per se good or bad, meaning it doesn't matter what you know, it doesn't matter what information you're collecting, information is always good or always bad. So if you want, this is my favorite egg chart, which is an invention of Nima. So let's think about giving information to the monopolist. There is a region on the left that information is per se bad. It doesn't matter where you are. It doesn't matter what information you give the monopolist. Surplus is hurt. There is a region to the right that information is per se good. Okay, so there is a region to the left, the right, where no matter where you are, no matter what information to monopolist you give, the information is good for the surplus. And there's a region in the middle where there is potential to be good or bad. Okay, so what I told you about the two extreme cases, what basically what Piku shows is that for two demand curves, and if you think about only giving full information, information is bad. So far, Piku, the only thing that we know so far about Piku is that it is here, because we know that for two demand curves, giving all information is bad. We don't know anything else. What about if there are many demand curves? What about we give partial information? BBM, on the other hand, because it exactly characterizes the optimal information, says that the information is generically, there is some optimal information here, okay? So we want to go more toward like characterizing this whole egg. So let me first start with the intuition of Piku. Let's take the two demand curves still, but allow partial information. What is partial information? Partial information means, okay, imagine there is a unit mass of consumers who had demand 2 minus P, a unit mass who had demand 3 minus P. Now, instead of perfectly separating them, let me create two markets. Let me segment them to two markets. The left market has 80% of the agents with lower demand curve, so and 20% of the higher demand curve. So the average demand curve that the monopolist faces is 2.2 minus P. On the right, it's the opposite. 80% of the people with higher demand curve, 20% with lower demand curve. So the average price that average demand curve the monopolist faces is 2.8. Now you can solve the same thing, okay? And then the bottom is no segmentation. So there are all the consumers in here. This is the demand curve the consumer that the monopolist face. You're gonna get the same results, basic equivalent of the result that I gave with like kind of full segmentation, that not being segmented is better for the consumer surplus. So the black area is higher than the sum of the red and blue. Now it's kind of clear that you can see that even for partial information with two demand curves, you can see clearly that the information has two impacts. Segmentation have two impacts. One is that it potentially changes the output, where in this case, in linear demand, it does not. The output is anyways 2.5 if you give some information or if you give full information, okay, no matter where you start from. But the output is sold at different prices. As I said, when you don't segment, everybody receives the output at the same price. when you segment people who have a lower marginal propensity to pay, they get it at a higher price, at a lower price. The ones who have a higher propensity to pay, they get it at a higher price. So in the linear demand curve, the output effect is 0, okay? But the fact that the output is so the different prices means that always the segmentation is going to be bad, okay? So always there's going to be fewer people who get a better price, but more people who get a worse price. And because the output is not changing, it's always bad. So now let's take that simple example. Let me limit myself to only 2 demand curves and say, okay, is it possible? So what did I show you here? That with 2 demand curves, if they're linear, information is per se bad for total surplus or consumer surplus. Okay. Now let me make the minimal change to this and see whether information can be per se good, or I'm making something like crazy up. And in fact, it can be per se good. Let me make a tiny change to the demand curve. The higher demand, I'm going to keep it constant, 3 minus P. What was the problem? The problem of misallocation was that, okay, the people who value the good less, they're gonna buy less, and they're gonna face a lower price, but they don't buy. They buy more, but when you give them a higher price, they buy less. But if you want the segmentation to be useful, you want them to buy a lot more when they're facing a lower price. So what do? I'm going to change my linear demand of 2 minus P to something that is slightly higher. Okay. So now an investor who does not really like the good, but a little bit like it, when he faces price P, he doesn't buy 2 minus P. He buys 2 minus P plus C divided by P. Okay. What is this term? So the demand curve is going to be a little bit above the linear demand curve. Okay. So why is this made up demand curve nice? Because the revenue, which is price times demand, is going to only have a constant term, okay, relative to the demand for the linear curve. So the optimal price does not change, which is the beauty of this thing, okay? So again, if your full segmentation, the optimal price is 1 and 1.5. The difference is that now for people who have a lower demand, they buy more. They buy 1 plus C instead of buying 1, okay? So now and then if you're not segmented, basically exactly the same as before, okay? So now the beauty of this thing is that I can basically control the quantity effect with 1 parameter C. So if the excess demand of the lower weak market, the lower type, is sufficiently high, then the benefit of price discrimination is high, okay? So it is not intuitively, although Pigou says price discrimination is really bad, you can already see from here that depends heavily on the shape of the demand curve, okay? So now what we do in that context is that we are going to characterize exactly when more price discrimination is per se good or bad with many types. Right now in the Pigou and the extended Pigou, I limited myself to 2 types. Now I'm going to allow many types. So what we're going to do is that we're going to have a reduction from the multi-type problem to one where there is only 2 relevant types. And then I'm going to give you necessary and sufficient conditions for the 2-type case. And through that, I'm going to highlight 3 distinct effects of information. Then there's going to be 1 slide that at the end that I'm going to talk about, like this result that I'm so excited about that I could not leave it out. But unfortunately, it's not yet in the paper because it's not complete, but it's about whether we can give a local improvement when neither one is the case. So that would be kind of an interesting insight about the whole intermediate region where information is not per se good or per se bad, and we cannot go all the way to optimize the optimal information, but we can give you local improvements. So With that, let me say what we do in the model, which is exactly bridging. We are hoping to bridge the classical and modern approach. As I said, the classical literature, starting with Pigo 1920, and Robinson, Maryam, and more recently with Aguiar et al., they have similar primitive as us. They have general demand curves, okay? They mostly limit to 2 demand curves, and they consider only private versus no information, no segmentation, which for us is equivalent to private to full versus no information. So the demand curve is kind of general. On the other hand, there is this modern work, BBM of 2015, that they have many demand curves with the thing that they have their only unit demand curves. So this is a unit demand, okay? What is specific about unit demand is that the type is the same as value. So if you know the type, you exactly know how much the agent values the good, and you can exactly charge them. So this can be perfectly when you give information to the monopolist, not only the type can be perfectly learned, but also the value can be perfectly learned. And now, but they go one step completely further, and they characterize the optimal segmentation, okay, which is the optimal level of information. And that we cannot do. Let me be very, very clear, that we cannot do. But what we do is that we're gonna, compare to the classical approach, we're gonna allow partial information, and we're going to also allow many types, similar to BBM. Compared to BBM, we're going to allow general demand curves. What is specific about general demand curve that you can see on the top is that type is different from value. So first-degree price discrimination is impossible. In a sense, another way that you can think about it is that type is what is maximally learnable, okay? So agents from the same type can still have heterogeneous values. Okay. And with that, here is the model. So there's going to be a single monopolist seller. There's going to be a unit mass of consumers. And theta is going to be the set of consumer types, which is a compact subset of linear vector space. Then we're going to allow demand curves. This general family, the wiggly D, is a family of demand curve. This is a function of P and the function of type, okay? What is type? You can think about type as the price sensitivity of the demand. For instance, if it's linear, price sensitivity of demand would be how much the demand is changes when the price changes. Another one.
Okay, it looks like we've lost the feed. I'm not sure if Maryam
Sorry,
will
what
know.
happened? I think
we've lost you for a second.
Sorry.
Can you hear me?
Yeah, I can hear you. Can you hear me?
Yeah. You've lost you for 15 seconds.
Okay. So
we are returning.
Okay,
I can almost see your slides.
Is this good? Should I start from here? Or you heard
yes,
this?
but I still don't see your slides. It shows that you are sharing, but yeah. I don't see the slides yet.
Maybe stop and restart.
Start again. Share. Did it work?
We still have a black. Oh yes, I can see it now.
Okay, good. I'm sorry. I'm on a university campus. I'm at NYU. I have no idea what's happening here. The one thing that I did not think was loss of internet. Okay, sorry. So,
glitches,
okay.
No worries.
So here is what we're doing, okay, which is we're trying to bridge the classical and modern. Did you hear this slide? Okay,
yes,
great.
we started the next slide as well.
Okay, excellent. So now let me tell you what the model is. There's going to be a single monopolist seller. There's going to be a unit mass of consumers. And theta is the set of the consumer types, which is a compact subset of linear vector space. Then there's going to be a family of demand curves, this wiggly D, which is a number of demand curves, which depend on the type theta. Okay. So what is the demand curve? Is the price sense? What is the type theta? You can think of type theta different ways. It depends. I have no idea. But some examples are like, one can be price sensitivity of demand. Let's think about a linear demand curve. Okay. So how much the demand of a single type changes with the price would be theta. okay? Another one would be, for instance, maximum demand. In the Pigu cases that I showed you, the type would be the maximum demand. Okay, how much with the minimum, with price zero, how much a consumer wants. A lot more relevance to non-theoretical economists, who like macro people who like me, is like elasticity of demand. Okay, how much, what the percentage of change in demand if the price changes by 1%. The simplest demand curve that I can tell you, that because we're going to use it as an example in the slides all the time, is CS demand. CS demand is one of the most this is a demand curve that is probably most often used in like macro. And so the elasticity of demand for CS demand is going to be the power of the demand curve. So we're going to make two assumptions, and we cannot relax them. Okay. One is that each demand curve is downward sloping. I guess that's fine. Okay. The second thing is that the revenue curve is going to be concave between 0 and the maximum price that can be charged. This is not without loss of generality, but for most purposes, I think it's fine. So let's take it as given. Okay. So now, let me talk about the seller information and his optimization problem. Seller is the monopolist. So let's mu denote a market, okay? What is mu? Mu is the full support probability distribution of types which are present in that particular market. And mu 0 is the prior distribution of consumer types. So imagine that's like a no segmentation. Now, what is a segmentation? Segmentation is distribution over the markets, okay? So, and what is important, we're going to impose that there needs to be base plausibility. So the expectation of being in a market, given any segmentation, should be the prior, okay? Then what is a seller optimization problem? Facing a segmentation, which is a couple of markets, the seller chooses a separate price for each market, so that for each market in that segmentation, the price of that market maximizes expected revenue of the seller conditional on being that particular market. So another very important issue that is floating around over and over again is that, look, we have different notions of surplus, and we care about different notions of surplus. Simplest, consumer surplus, and total surplus, okay? So we wanted like a method which is like very consistent to think about all of these things. Sorry, so I think now it's full screen, right? I'm sorry, it was not full screen, I think. Okay. So we want a consistent way to think about this. And it turns out that for us, we can very nicely characterize any alpha-weighted surplus. What do I mean by alpha-weighted surplus? What are the parts of the surplus? The parts of the surplus is the revenue of the seller, okay, and the consumer surplus, okay? Now let's weight them. Let's put alpha weight on the consumer surplus and 1 minus alpha weight on the revenue, okay? That we're gonna call alpha weighted surplus of a particular type given a particular price, okay? Now, if you wanna find the alpha weighted surplus of a particular segmentation, you have to take the integral over each market in that segmentation and over each market over all the types that are in that market, okay? So to simplify, what is consumer surplus in this market? If you set alpha equals 1, that is consumer surplus, right? Alpha equals 1 kills this term, okay? That's consumer surplus. Now, what is total surplus? Alpha half, okay? Alpha half would be half consumer surplus, half R. And not only that, but we can talk about any alpha. It turns out that our results generalize to any alpha, okay? So what are we looking for? Now, with this setup, this is the main question that I'm going to spend like all the talk on, except one slide. So I want to think about, when is data per se good or per se bad? What is that? That means monotonic impact of information on alpha surplus. So we're going to call information monotonically bad, or IMB. I'm going to use this, and I'm going to try to always have it in red throughout the slides. If for every two segmentations, sigma and sigma prime, if sigma is primary or sigma prime, meaning it's a mean preserving spread of sigma prime, then segmentation sigma gives a lower surplus. That means, intuitively, if you give more information to the seller, to the monopolist, it can segment more, finer, then the alpha surplus goes down. Alpha surplus can be consumer surplus, can be a producer surplus, can be anything in the middle. If alpha is 0, which is revenue, this is definitely, information is never bad for revenue. Alternatively, the opposite case is information is monotonically good, or IMG. If, again, for any two segmentations where sigma is finer than sigma prime, sigma increases the surplus. Let me go to my favorite graph. Remember, I said on the left, information is per se bad. That means alpha IMB holds. Whenever you give information to the monopolist, information is monotonically bad for alpha surplus. On the other end was when information is per se good. So information monotonically increases alpha surplus. Okay. So let me tell you the results. This is the main result. Okay. Aside from the last slide, this is going to be the main result. So I'm going to spend the whole time talking about this. So let's take a family of demand curves. This is the wiggly D. Okay. Which has a family, many demand curves, which are parameterized by a parameter theta. Let D1 and D2 denote the two demand curves that have the highest and the lowest monopoly price. Now, let's read everything with alpha IMB, and then alpha IMG is going to be exactly the opposite. Okay, so alpha IMB holds for this family of demand curve if and only if, so these are necessary and sufficient conditions. Okay, so I'm going to exactly characterize the barriers in my egg graph. If and only if, one, there is a partial inclusion, meaning for any two demand curves, the optimal monopoly price for that full information demand curve falls between the maximum and minimum of the prices that are acceptable in the other demand curve. Then, so let's take that as given, let's take partial inclusion as given. Okay, then we go to the core two parts of the theorem. First, there exist two functions, which we'll call F1 and F2, that every one of these demand curves, imagine there can be like a million demand curves, okay? Every one of these demand curves can be written as an additive and multiplicative function of the two function F1 and F2 of the type, okay? And two demand curves that do not depend on the type, okay? And second condition, then alpha IMB has to hold for these two only demand curves, okay? So now it turns down, now I have reduced the question, the problem to two demand curves. Now, when is it that alpha IMB holds for two demand curves? Okay, this complicated equation that I'm gonna go over, okay, if it is decreasing between the maximum and minimum monopoly price, okay, in this family of demand curves, if this function is decreasing, then alpha information is monotonically bad for alpha surplus. Then now what about alpha? When is information monotonically good? The first condition is the same. Still, there should be that every demand function should be able to, you should be able to write every demand function in two bases if you want, two bases of demand. But the only difference is that information is monotonically good for two demand curves if this complicated function is increasing. Okay.
Maryam, for part one of the statement, you're saying that these conditions have to hold if either alpha IMB or alpha IMG holds?
No, alpha IMB holds. So ignore all the alpha IMG in here, okay? Alpha IMB holds if and only if there's partial inclusion, there exist two functions F1 and F2 that demand curves can be, every demand curve can be written like this. And alpha IMB holds for these two demand curves, which requires this expression to be decreasing on the maximum and minimum.
Okay, so you're saying alpha IMG is the same thing except that part E.
This, exact. That's exactly what I'm saying.
Got it.
Okay, great. Sorry. So going forward, let me suppress the alpha through the slides, except for one result where it's about alpha, change in alpha. Everything that I say, I'm gonna call IMB, IMG, I'm gonna call V, okay, and V alpha is this alpha surplus. It holds for every alpha, okay. Then, okay, so now before like opening up each of these things, let me tell you about partial information, partial inclusion. I'm not gonna talk about that in detail. It is a direct, basically application of part of the argument in BBM, okay, that basically if there is a demand curve that is not being served at all in the segmentation, in the no information, basically giving no information to the monopolist, it's better to take that one demand out, okay, put epsilon of every other demand to that segment, okay, then the monopolist is going to be happy, okay, and that demand is going to be served, okay, so everybody is going to be happy, okay. So let me take partial inclusion as given going forward and talk about the other two conditions. First, let me talk about the separability condition, okay, which is the kind of the weird one. So this is the kind of most theoretically challenging part of the paper, and the starting point is actually the great work of Alex and his co-authors on strong duality. They have introduced strong duality very nicely from mathematics into solving economic optimization problems. So in two papers, one by Wolitzky in 2018 and the more recent paper of Alex and Corral and Wolitzky in 2024. So we're gonna just take that as given, okay? We're gonna show that their main theorem, okay, applies to our setting, and we're gonna take it from there, okay? So next, we're going to say, okay, how do we apply duality to the optimal information, to seeing whether, to checking whether no information is giving no information to the monopolist is optimal for surplus, meaning information is IMB, okay, or IMG. So the first step is this proposition. Let's take an optimization U. We want to maximize U, which is a price of which is a function of the price and the types. A distribution G maximizes the subjective function if and only if there exist two continuous functions, lambda and psi, such that these two equations hold. So let me first say, what is U? Why am I using U? Because I want this theorem applies, this proposition applies equivalently to IMB and IMG. The only difference being that if you want to apply it to information being monotonically bad, U has to be V, okay, the surplus. If monotonically good, it has to be minus V, okay. Now, what are these two conditions? If you stare at these two conditions just look like Lagrangians. Okay, so it is kind of the first one is Lagrangian when on the optimal set. Okay, the second one is Lagrangian when it is not optimal. Okay, so how do we get this? Let's first take a particular prior. Okay, then for any particular prior, okay, giving no information to monopolists is optimal if and only if the price that is posited is maximizing the Lagrangian multiplier, which is basically the V, okay, minus the Lagrangian term that is the monopolist have to have its revenue, the first order condition of the monopolist have to hold. Okay. So this is for a particular given prior. Now we know that IMB is holds, meaning information is monotonically bad for a surplus if this holds for any information that you start with. So for any, it doesn't matter what prior you're starting from. For a single, there is going to be a single monopoly price, which means the monopolist should not be able to price discriminate at all. Then that means that for any prior, we should have the function side such that for every theta, that monopoly price maximizes the objective of the Lagrangian. So let me give you the intuition, the very, very simple intuition from the discrete problem. Assume that there is a demand, there's a set of demand curves that are discrete, as I said. So, and they have different prices, P1 to Pn, okay? And each of the demand curves corresponds to a particular theta. So there's going to be, the theta is going to be between theta 1, there's going to be m thetas, okay? So this is all the types, okay? And the first one is all the markets, okay? So there's I markets, and each of them have a distribution, can have a distribution of the m types. And imagine that the prior is, let me call it h of theta I, okay? Now, it turns out that for a discrete problem, the maximization problem becomes a beautiful linear program, okay? What does the monopolist, what's the maximization problem? The maximization problem is to maximize the surplus over what is the distribution of each type in each of the markets, okay? Such that, of course, for given across all the markets, the measure of agents of type I should be exactly the prior, okay? That's base plausibility. Then for in each market, the monopolist's choice of price have to maximize his revenue, okay? And then, of course, the probability of being on all the markets is 1, and you cannot put negative agents in each market. And now the two Lagrangian multipliers very simply follow. Lambda j is the Lagrangian multiplier on each agent, base plausibility, and psi I is the Lagrangian multiplier on the optimality of monopolist pricing in each market. And so now we can write this again. So now for simplicity, let me show you IMB for only consumer surplus, okay? Because that's gonna make my life simpler. So when is information monotonically bad for consumer surplus? When there is a single price, P bar, which maximizes consumer surplus, okay, minus the Lagrangian term, when the first order condition. So what is the first order condition? The first order condition is take the derivative with respect to P, okay? So and we want the first order condition to hold at the unique monopoly price, okay? So let me put the unique monopoly price in. When you put the unique monopoly price in, and we need to show that this first order condition holds for a single monopoly price. That boils down to showing the existence of the function psi, okay? And what we need is that if the optimal monopoly price is that unique price, we need to have the psi, the Lagrangian multiplier at that particular function. So at that particular price. So now rank the thetas in the increasing order of their monopoly price, P star, if there was full information. We know that if the markets are, if there's full information, the monopolist marginal revenue is 0 at that particular monopoly price of that particular type. Okay, so this equation holds market by market if the market is full information. Okay, so now because I've ranked the thetas, I can exactly know that this is always the same price. Okay, so now if I rank them for for any theta where the price is where its own monopoly price is below the monopoly price with no information, the revenue, the marginal revenue at the monopoly price, no information monopoly price, is past the peak, so it's falling. For any demand curve, any type whose full information monopoly price is above the no information monopoly price, the marginal revenue curve is still increasing. Okay, then you can do like, then you're gonna shrink this because there's like many of these curves. Okay, and then at the limit, when we take the limit of theta going to the hypothetical theta bar, which is the type for which P bar would be the optimal full information monopoly price, we can use the L'Hopital rule, and we can characterize the Lagrangian multiplier at the no information monopoly price, and it's going to be constant. So now you're going to be saying, okay, why did you do all of these things on the slides in a talk, which is an hour? The reason is that this is going to help me show you where we get the separability, which is my favorite result. Okay, so remember, this was the first order condition. So now I know what is this Lagrangian multiplier at the optimal monopoly price. I'm going to put it in. Okay, so now I know that for information to be monotonically bad, I need this equation to hold for every single type. Okay, that's why I'm using the surplus to be consumer surplus, because when V is consumer surplus, derivative of V with respect to P is very nice. It's going to be minus RP. So then this equation, which used to have P in it, V in it, now it turns down to a second order linear ODE for each R in terms of, for each theta, only in terms of the revenue function. Okay, a second order differential equal linear ODE in for any function has only the fundamental theorem of homogeneous linear systems tells us that it has only two solutions. Okay, and that gives me the two bases, F1 and F2 of theta. Okay, so now what does this say? This says any revenue function, okay, any monopolist revenue function that satisfies this equation can be written in two bases of F1 and F2 of theta with two multipliers which depend on P, which we're going to call them D1 and D2. Okay, so those are going to be my base demands. And then, of course, because D is revenue divided by P, okay, now this exactly goes back to the D. So this tells you that any family of many thetas, that any family of demand curves that you give me with any number and any demand curve, in order for IMB to hold, for information to be monotonically bad or monotonically good, if you multiply everything by a negative, it should be that every member, every D that is a member of that family should be able to, we should be able to write it as an additive and multiplicatively separable functions of the parameter of the type theta and two demand functions D. The beauty of this two is that with two demand curves, we have very, very nice techniques to characterize when is information monotonically good for two demand curves or not, okay? And for that, we're going to use some variation of like concavification So now we have only two demand curves, okay? I have to say whether information is monotonically bad for these two demand curves or not, okay? Which were like these two bases, D1 and D2. They don't depend on the type, okay? So let's take any distribution between them, mu, weight mu on demand 1 and 1 minus mu on demand 2, and define the price of that mu and if you want the the welfare of that mu as basically this is a market which has mu of type D1 and 1 minus mu of type D2. So the first order condition of the monopolist should hold, okay? And with that first order condition, the optimal the valuation is going to be the weighted sum of the valuation under demand 1 at that price and valuation under demand 2 of that price. Okay, you can see that the types do not enter here. Okay, so now when does IMB hold? When W is concave. Okay, when you don't want to give any information, you want to stick to mu 0. Okay. So what is W concave? That means W prime should be decreasing. Okay. What is W prime? It's the difference between the derivative between the two demand curves, between the two valuations, plus the expectation of their derivative times the P prime of mu. Okay. So this is just simply saying that if you want the no information to be optimal, the W have to be concave. And W prime of mu is basically the complicated equation that I had there, okay? Which, if you remember, was the difference between the value at two demands, okay, and some complicated expectation weighted by the derivative. So with that, now that hopefully I've completely unmantled all that theorem that looked kind of complicated, but actually is exposed. It's kind of simple. Let me talk about the three effects of information. And I'm going to go very simple here again. Let's assume we have two types, okay? And before giving any information, they were all in the same market. They were all facing the same price, P. And imagine that the two were like both equally likely. Now we're going to divide them into two markets. In market 1, we're going to, and that's the after, we're going to put 2/3 of the type 1 and 1/3 of the type 2. In market 2, we're going to put 1/3 of type 2 and 1/3 of type 1 and 2/3 of type 2. This is a little similar to the exercise that I did for you in the beginning for Pico. Okay. So let's assume that the demands are such that price 1 is lower than price 2. Okay. And they're both, and by base plausibility, they're going to be on the two sides of the average price P. Okay. So now there's going to be three effects. How do I characterize this three effects? I can characterize the three effects by basically look at the second derivative of the W function. Okay. The three effects are: 1, there's going to be a within type price change effect. Now, this is not full information. Type 1, some of them are going to face P1, some of them are going to face type P2, the price P2. The second thing is that the cross type change effect. On the top, before, both types were facing the same price. Okay. Now they're going to face different prices. And the third thing is the price curvature effect. Okay. So, okay, so sorry, this is exactly as I said. And then basically, the price curvature effect is really what was making with linear demand curves dominates, okay, and make giving information always bad, because basically the size of the drop of price and increase in prices in different markets is different, okay, and if there is full information, it's always too much with linear demand, okay? So let me talk, okay, so let me talk very quickly about the implications, okay? The implication, so, yes, yes.
Sort of a big picture, I guess. So it seems to me that your results are very much about, or kind of boil down to when you have two markets, when you want to pool them or separate them.
So, well, it's partial. So one thing is that it's partial pooling and partial separating.
But I thought your conditions are for when you either always want to pool all the way or separate all the way.
Yes, yes, yes. So yes, that's correct. Yes, yes,
Right.
yes.
Right. And my understanding is that's also the exercise that like these old papers are interested in. And so I'm curious how your conditions relate to their conditions.
Okay, so there is a little bit of difference from what these papers are thinking. So these papers don't think about you always want to give information, okay? They're about like there's this one prior, okay? And you want to give full information, okay? We think about, okay, maybe you know something, okay? And then you want to, no matter what you know. So in a sense, it is correct that if for every prior, any of those papers work, yes, that's exactly equivalent. This is exactly for every prior, exactly. In that sense, that's exactly right. Okay. So now what is the difference between us? Let me give you, okay, because Alex asked this, let me give you the difference that I really, really like. Okay. So here is the difference that I really, really like, because it's about the empirical evidence, and it's about CES demand. Okay. Let's limit ourselves to two demand curves. Okay. This is CES demand. I can tell you with many demand curves, CES cannot be reduced to additive multiplicative. Okay. So for sure, for many CES demand curves, we can't say information is monotonically good or monotonically bad. Okay. So let me limit to only two demand curves. Okay. And this is something that none of those papers can talk about. Okay. We can actually exactly say that for CES demand, okay, if so two different CES demands, okay, that have, with me, they have two different elasticities, okay. Imagine that the elasticity of theta 1 is higher than elasticity of theta 2, which means its price is lower, okay. Then what is 1/2 IMB? That's total surplus, okay. Information is bad for total surplus if and only if theta is far away, the two elasticities are more than half apart, okay. Means more important. So, and what is nice about this, the nice thing about this is that we have this other result that if alpha IMB holds, okay, for any alpha, if information is monotonically bad, it's bad for any higher alpha. Simplest implication, if information is bad for total surplus, it's definitely bad for consumer surplus, okay? And what we're telling you is that with two demand curves, okay, which are both CBS, if the two elasticities are close, are not too far, okay, and for all empirical estimates, they're not too far. Half is a large number, okay? Most empirical estimates put difference in elasticities in 0.1, 0.2, depends on the good too. But if the demand elasticities are not too far, then information is not only bad, is monotonically bad, not only for the consumer surplus, but also for a total surplus, okay? And again, this is a strong if and only if statement. The other more general difference is that there are only sufficient conditions, okay? We have necessary and sufficient conditions. And sometimes, like in the paper, we do this that, like, for instance, in Aguiar et al. That has a lot of these sufficient, like prominent sufficient conditions. We exactly say when is it that their sufficient condition never holds, okay? While for us, like, and we can, or their sufficient condition always holds, okay? But the necessary and sufficient condition does not hold. So kind of the nice thing is that, so let me jump to my last slide because I'm out of time, but I'm going to use one more minute. Okay. So this is, let me start from, let me go back to the egg chart that I said, okay, and introduce our last result in that too. As I said, there is a space where information can be per se bad, as Alex said, for any, it means for any prior, giving full information is bad, okay. There can be information being always good, mean for any prior, or anybody to start, it's good. And then there is a state in the middle that we don't know. What we do compared to the other papers, they characterize sufficient conditions, okay, about where these sidelines are, okay, when information is monotonically bad, and sufficient conditions for information being monotonically bad or monotonically good, okay. So the first thing that we do is that we characterize these two lines fully, okay. So for us, it's necessary and sufficient condition. Then you might still argue that, okay, that is kind of a small space, okay. And we don't, most of those go also for two. We also, I think one thing that I really like about our paper, we kind of say that, okay, going to two is actually, thinking about two is actually not such a bad idea, okay. Because from many demand curves, you can actually reduce it to two. So that is kind of a nice thing that I think we say, okay. But beyond that, you can say, okay, but this space is small. What about everything that is in the middle? Okay, and BBM is everything, is something exactly in this middle, okay? BBM says, okay, where information is sometimes good or sometimes bad, if you limit yourself to unit demand curves, then we are going to characterize the globally optimal information in the middle, okay? We cannot do that. What we say instead is that, let's say we are in the middle, we're not going to limit ourselves to linear demand curves, but take two demand curves, which are general. We can always provide a local improvement to information at that point. Local improvement giving information or taking away information, okay? So that, let me finish by saying that this is a paper which is about, primarily, it used to be, hopefully now it's going to be, I'm so excited, it's going to be talking about the middle too, whether the information is per se good or per se bad. And we show a reduction from many types to two types. And then we're going to give necessary and sufficient condition formulas for the two type case, which captures three distinct effects of the information. And then if the new part is, which I did not talk about much, is that whether what happens in the middle when the information can be good or can be bad. We cannot characterize the optimal information, but we can give local improvements. And methodologically, this applies the modern framework, which is the endogenous segmentation and tools like concave aggregation and duality, to study a very classic problem of like people with many demand curves, whether information is good or bad. Now, you would ask exactly whether per se good or bad information are strong properties, whether these conditions are restrictive. So, I mean, yes, separability is a strong condition, okay, in a formal sense. However, I'm going to argue that it's empirically relevant. Okay, so I didn't get to talk about it, but we characterize like families of demand functions, okay, for which actually separability holds, okay. And in fact, we can get regions for which information is monotonically good, monotonically bad, or neither, okay. So we see the relevance of this to general problems. Furthermore, empirically speaking, very often we approximate demand curves by two. Okay, so in that sense, approximating demand curves with two, but giving very precise results for general demand curves is kind of very interesting. And lastly, we're going to give local improvements when this is not the case. So hopefully this is, despite the restrictions, this is going to be a useful framework to build on a lot. Thank you.
Thank you very much. This was great. Given the time, I think we are not too late. So
I'm sorry.
we are moving. Yeah, that's fine. That's fine. This is great. I think the common custom is to start the Q&A session with our panelists, or if there are any comments, that's also suitable. But the rest of the audience, please get ready for your questions. I think Stephen is unmuted.
Yes. a question I was going to ask is whether, so I think it's very cool, the fact that given that the literature, the classical literature is written about the two markets case, it's very cool that you have a theoretical result, the reduction result. But it wasn't so obvious, maybe except until the last bullet point on that slide, exactly how you interpret this condition. So that is the two market, the reduction to two markets.
Yes, yes.
So, you know, I could see some people saying this is this, you know, you could interpret the result as saying that your IMB and IMG properties will never hold, because it would be a remarkable property that you had the two market reduction. Now, you said you had examples, so these are examples, are they?
Yes, this is one of the examples. This is one of the examples that is kind of nice because it basically shows that how we can go from it both has like the total surplus and consumer surplus in it, and it also switches between good and bad information. Okay, so this is basically saying, okay, let's take a demand curve, whatever demand curve that you want, okay, and change the marginal utility, okay, this marginal willingness to pay and maximum willingness to pay. Assume that those are the things that are governed by the parameters, okay?
That are
Like,
governed
not the
by,
elasticity of substitution, by the type. What type governs is the marginal willingness to pay, okay, and the maximum willingness to pay. For instance, not the elasticity of substitution, okay?
Got it.
If that is the case, then we can say lot, okay? It's a question of how much the big thing holds, or the reduction holds, depends on really what is governed by the type, okay? And that's why in the beginning I brought this example of the type governs different things, okay? If you think the type governs elasticity, tough luck, okay? If you think type governs marginal willingness to pay, much better. If you think type governs maximum willingness to pay, great. So, although the demand curve can be different, you see, this is not a linear demand curve. This can be like a weird demand curve, anything. Okay.
Sorry, if I may, can I add just one thing, Stephen?
Yeah.
So I think I agree with you that on the face of it, the result basically says, you know, no family of demand we should expect to satisfy this property. However, so I think about it slightly differently, which is that it's identifying an extreme case. Now, how far you are from this extreme case for an arbitrary family of demand essentially is a quantitative question. And so this approximation results that Maryam mentioned which unfortunately we do not have, and we hope to have it very soon, is in essence trying to identify the answer to the quantitative question. So in other words, if you give me a family of demand curves, what exactly is that I need to measure to know its distance from a two basis family in some sense. And so that I think we are able, I am somewhat certain, I think, that we are able to at least give the somewhat quantitative answer of, well, you have to look at this eigenvalue of some matrix, which I think would actually be the next step, which is that why is it that we care about this result? Because it identifies the extreme point and the quantitative sort of calculation that needs to be done. So that's perhaps a bit more, detailed answer.
Okay. And one other question is you had the dividing it into three effects, one of which was the price elasticity. I have the idea that Robinson moved beyond linear demand curves and was talking about curvature. I'm just wondering, with the classical literature and Aguirre, I don't know how you say the name, and his co-authors, is kind of the most general, or they certainly claim that they're the most general result with Robinson's logic in it. But I wonder, in those arguments, what these three effects? So I kind of think this effect they talk about, there must be some connection, but I don't know.
So yes, there is some connection. Okay, and as I said, so we kind of to kind of relate a little more to them. Okay, what we do is that we also provide sufficient conditions. Okay, for this to hold, which is not, the children not necessarily hold. And that would be exactly when all of these, our sufficient conditions are exactly when all three of these forces go the same direction. Okay.
Okay.
So in that sense, we can make a connection with them, okay? But I see the strength of our results as saying, okay, although we can characterize these three, because we're giving necessary and sufficient, we can also talk about the cases where they go different directions, okay? And how they should be incorporated together, okay? And that's where there are sometimes that they give a sufficient condition that is not relevant, okay? Because that sufficient condition is always violated.
Mm-hmm.
But like because for us it's necessary and sufficient, okay?
Yeah, got it. So, and do you know of that sometimes you're using, so they talk about the comparison between no information and full information. You require monotonicity everywhere in between. So that is the reason why you get necessary and sufficient conditions, and they only get
that is
sufficient
the
conditions?
reason that we get, exactly. So the fact that we get necessary and sufficient condition is basically this optimization problem, okay, which has to hold for every p and every mu and so there is going to be one price for everything, for any prior. It's going to what Alex said, okay? It has to hold for every prior, which means which is equivalent to saying it's always good or always bad, okay? And we thought because it's regulatory, it's very hard to control, okay? It's pretty impossible to control. So we thought this is the relevant case, as Ali mentioned, to start the baseline from, okay? And think about, okay, if you can control to some degree, how far from that you would be.
Yeah, very good.
Can I just say something? I think going back to what Alex was asking. So we are giving exact conditions for information to be monotonically bad, say, which, as Alex said, implies under our conditions, if you compare full information to no information, full information is worse than no information. So we are giving sufficient conditions for full information being worse than no information, and the classic literature also gives sufficient conditions for that. But because now both of these, what we are giving and what literature identifies, are sufficient conditions for full information being lower than no information, there is no, none of these results imply the other one.
Thank you. Alex, any last comments?
I mentioned just briefly another connection with our paper, which also relates to what Stephen said, which is that we have this result that in this class of persuasion problems, even for a given prior, no disclosure is generically suboptimal once you have more than two states, which here is like more than two markets. So that kind of already suggests that it's going to be a very restrictive condition for no disclosure to be optimal, even for all priors. We also have a characterization of that for some other classes of problems that don't include the one you have here, but just like, kind of when you have a concave problem like this where the receiver's first order condition is necessary and sufficient, just like that, that you would have that no disclosure would ever be optimal is kind of a non-generic condition. So it's shouldn't be too surprising, I guess, that it's a very restrictive condition.
Yeah, I agree. I think perhaps this is maybe for the sort of nerdy audience, but I think we're basically giving a characterization of the generic set, right? And this is what we are doing. But you're right that it's not. You guys have shown that this is generically no information is not optimal. We're also saying even generically full information is not optimal, and which is not surprising because one is about concavity, one is about convexity of the value function. But I think we're basically on the technical side, we're just characterizing this set where those things are true, as opposed to
clarify, that's an interesting difference, I think, between your setting and our paper, right? Because in our paper, full disclosure is not generically suboptimal, but your problem is
because we have the rank condition. So technically,
in your setting, it's not.
Is that the rank condition is violated, and so that's why
Exactly.
we have this pay. So in other words, because these payoffs are effectively quote unquote in a function collinear, the payoff of the sender and receiver, they're generated by the same sort of revenue / demand function. Then that's why we sort of violate the rank condition from the get-go. And so we are, for this application at least, I think we are giving a full characterization of that set.
Yeah. And then,
because we are sort of run out of time, I'm going to say the official goodbyes, but please stay after that because the conversation will be going on. So thank you, Maryam, for joining us today. See you all next week. Thank you, Alex and Stephen, for coming, and co-authors, Nima